Hello everyone, welcome to Waves question 6. Now I'm not going to go through Waves question 1 through 5 because they are too simple. Let's take a look at Wave question 6. Now over here we have a wave of wavelength 6 meters propagates from P to Q. So let's just put down the displacement and distance graph. So this is a wave of wavelength 2 meters, okay? Over here is 2 meters. So this point is P. Now what about Q? Q is somewhere really far away over here, and the distance from P to Q will be 10.2 meters, 10.2 meters. So the question is, what is the phase difference between P and Q? Now let's talk about what is the meaning of phase difference. Whenever you hear the word phase, it's just equivalent to the word angle, all right, phase angle. Now if we take a look at Z, this is a sine wave. Sine wave, this will be equivalent to 360 degrees, all right, for a sine wave, because a sine wave finishes one cycle at 360 degrees, or actually 2 pi, okay, 2 pi or 360 degrees. So over here we have, right, 2 pi or 360 degrees is equivalent to 2 meters. So what is the angle equivalent that is equals to 10.2 meters? Now, in order to do this, we can just see how many times does the phase, does 360 degrees happen. So one way that we can do it would be 10.2 divided by 2 times 360 degrees. Now this is going to give us 1836 degrees, which is way above, but because the phase must be in between, is written from 0 degrees to 180 degrees. Okay, so that means to say you have to write a number that's between 0 and 180. So what you would do is to take 1836, right, in minus 360, minus 360, minus 360, minus 360, and minus 360 again, and you end up with 36 degrees. So this is the answer. But in physics, we don't really answer in terms of degrees. We always answer in terms of radians. So let me show you the correct answer. How do we write down the phase? Okay, so the phase of the oscillation will be equals to the wave number multiplied by the difference in the distance. And the wave number will be 2 pi divided by the wavelength multiplied by the difference in the distance. So this will be 2 pi divided by 10.2 multiplied by, divided by 2 multiplied by 10.2. And this is going to give you 10.2 pi. Now, so we need to subtract the 2 pi's. Therefore, since the phase must be between 0 and half a pi, so if we keep subtracting 360 degrees all the way, keep subtracting 2 pi, that will make you end up with 0.2 pi, which is equals to 0.628 radians. Okay, so that's how you do question number 6. Now let's move on to question number 7. The diagram shows the variation with distance d along a sinusoidal wave of displacement of particles in a wave. The amplitude of the wave is y0. What's the phase angle between the two particles P and Q in the wave? Now let me just go back to a sine wave. Okay, let's go back to a sine wave. And over here, okay, this is y and then this is x. So this is A. Okay, so the question is, what is the angle that gives you half A? Okay, so you get y equals to A sine x. So when x equals to how many degrees? Y equals to A over 2. Now, all of us know that when x is equals to 30 degrees, then your sine function will be exactly half, because sine of 30 is equals to half. So what this means is that this must be 30 degrees. Now, if this is 180 degrees, and then over here is, minus half A, then this must be how many degrees? It's 180 plus 30. So this must be 210 degrees. Okay. Now, let's, then what is the difference between P and Q? P is here, and Q is here, right? So the phase difference between P and Q will be 30 degrees. So there's really no need for super complicated working over here. Okay, so what about if it's not exactly half? So let me give you an example over here. Okay, what about if it's not exactly half? Why don't I give you yx, and then I'll do something like this is A and this is 0.6A. So what is the phase difference between these 2 points? What is this angle over here? Okay, so the phase angle, you can find it by saying that 0.6 is equals to sine of x. So x will be equals to the arcsine of 0.6. And that should give you 36.9 degrees. So therefore this point is 36.9 degrees. So the phase difference between these 2 points, phi, will be equals to 36.9 degrees. Okay, so it's as easy as that. All right, so that's question 7. Let's move on now to question 8, intensity. Now, I just want to remind everybody that intensity will be the power of the source, okay, the power of the source divided by the area of the light that is shining, okay. So in this case, this is the area number 2, this is the area number 1. Okay, so waves from a point source pass through an area 2 cm wide as shown. Within this area, the intensity of the waves is I and the amplitude is A. Okay, so the next thing that I need to teach you is the intensity is proportional to amplitude squared. And then the amplitude, okay, the amplitude is proportional to intensity square root. Okay, so you need to use all 3 of these ideas. Now, so within this wave of 2 cm, the intensity is I and the amplitude is A. The waves reach a second area of width 16 cm. Okay, what will be the intensity and amplitude when they reach the second area? So let's take a look. Now, let's call this length our unit U. Okay, unit U. I don't know how big is this box because it never said so. But using the idea of similar triangles, you notice that this 2 cm becomes 16 cm. So that means you multiply by 8. So that means this also must multiply by 8. So this is 8U. So let's talk about the area. The area, this is times 8 and this is also times 8. That means the area A1, you multiply by 64 to get area A2. Okay, because you multiply by 8 for the breadth as well as the height. So if the area will be multiplied by 64, therefore the intensity 2 will be 1/64 of the intensity I1. Okay, so the intensity will be 1/64 of the intensity of I1. What about the amplitude 2? The amplitude 2 will be, okay, square root of, because the amplitude is square root of intensity. Okay, square root of 1/64 of the intensity I1, which will be 1/8 of the amplitude A1, amplitude 1. Okay, so that means to say that the intensity is 1/64, the amplitude will be the square root of that. So the answer will be C. Amplitude is 1/8 and intensity will be 1/64. So that's question 8. Let's move on to question 9. Question 9 is a pretty long question. So this question, we have to talk about several concepts, okay? Now, a satellite transmits microwaves in all directions. The power output of the satellite is 60 watts. What about the dish area on Earth? How much power does it receive? Now, so first of all, we need to talk about intensity and power. Okay, so this is a light bulb with a power of P light, power of P source. Okay. Now, the light bulb transmits power in all directions. So the light will spread out and it will be a sphere. The light will spread out in the shape of a sphere. Now, this is a small area over here, area of the sphere. area. Okay, now the intensity at this point, the intensity is equals to the power of the source divided by the area of the entire shape of the light. The area of the light is equals to a sphere. So that means the intensity will be given by the formula power of the source divided by 4 pi r squared, where r is the distance from here to here. This distance is r, radius of the sphere of light. Okay, so what does this mean? This means that further from the source, the intensity drops. How about power at the receiver? So let's say that there's a intensity now. Okay, now this intensity I, this light of intensity I, is going to hit a piece of paper of area A. Okay, let me just redraw this more properly. Okay, so this is a piece of a receiver. Okay, a rectangular receiver. This is the normal to the surface, and let's say the signals from space. Okay, so the radio signal. So the radio signal, okay, is approaching and is hitting the receiver at a particular angle theta. Okay, so over here, the radio signal intensity is given by IS, radio signal intensity. The area of the receiver is given by area A. So what is the power that is received? The power received, okay, is given by the formula P is equals to intensity of the radio signal multiplied by the area of the receiver multiplied by cosine theta. Okay, so this is the formula for the power received. Now, so what does this mean? This means that as the signal travels further, the intensity of the signal becomes weaker. As signal travels further, the signal intensity will become weaker. Now, what about on the other side, the receiver? So how do you get a good power received? To get more power received, you need more area. You need more area, or you need to angle it such that it's perpendicular to the signal. What I've drawn over here is perpendicular. All right. So some of you may not be able to see, so I'll just raise it up again. Okay, so these two equations are what is going to help us, okay, for this question. We will need these two questions. The first one is the intensity of a signal as it travels from the source, and the other one is the power received by an area. So over here, let's take a look. A satellite above the Earth transmits microwaves uniformly in all directions. The power output of the satellite is 60 watts. What is the power received by a dish aerial with an effective area of 260 square meters? So first of all, we need to answer this question, we need to find out the intensity of the signal. The intensity of the signal will be the power of the signal divided by 4 pi r squared. And r is 3.6 times 10 to the power of 7. All right. So the intensity of this signal will be 3.684 times 10 to the power of minus 15 watts per square meter. So then the power received, okay, which we assume that is perpendicular, theta equals to 90 degrees. Sorry, theta equals to 0 degrees. Right, will be the signal IS multiplied by area multiplied by cosine 0. Okay, that will give us the maximum power. Okay, 3.684 times 10 to the power of minus 15 multiplied by 260. Let me just move this up so that you can see it. All right, and that will give me an answer of 9.58 times 10 to the power of minus 13 watts, which is a very small signal, but nowadays with a very good computer equipment, you can manage to decode this signal even though it's very weak. Now suggest why a reason why the actual power will be less than that calculated in A. As the microwave enters the earth, the energy of the microwave is dispersed, or the correct word is attenuated. The correct word is attenuated due to interaction with the Earth's atmosphere. So some of the microwaves are absorbed. Okay, so if the output power of the satellite is quadruple, what would happen to the intensity? Now let's work out what is the power received. The power received will be the power of the satellite divided by 4 pi r squared multiplied by the area of the receiver, okay, multiplied by cosine theta, which we assume will be perpendicular. So if the power of the source times 4, then the intensity of the source will be also times 4. Okay, so the intensity will be equals to times 4 as well. But what about the amplitude of the signals received by the dish? Remember that amplitude will be proportional to the square root of the intensity. So therefore, the amplitude will increase by 2 times. Okay, so what happens is that the intensity will be increased by 4 because the power of the satellite increased by 4. Then the amplitude will increase by 2 because you put in 4 times more intensity and you square root it over here. The amplitude increases by 2. So that's the end of question 9. If you have any questions, you can ask me to demonstrate this in class. Let's take a look at question 10. A point source of sound emits equally in all directions at a constant rate. So the person is 8 meters from the source. After a while, the intensity of the source is halved. So you have to calculate the distance that he should be if he wishes the intensity to be as loud as before. Now let's take a look at the relationship between intensity and distance from the source. So the intensity will be the power of the source divided by 4 pi r squared, where r is the distance from the source. Now let's take a look at what happens if the distance doubles. If r is doubled, then intensity will become 1/4 of the original intensity. Okay, so I hope you know why that happens. Let's say I2 is equals to P over 4 pi 2r squared. This is equals to 1 over 4 times P over 4 pi r squared. This is 1 over 4 of I1. So what happens if r is doubled is that the effect on the intensity will be quartered. So if r doubled, intensity will be 1/4. What if r is half? If r is half, okay, if r is half, then the intensity 2 will be 4 times that of intensity 1. Okay, so what relationship is this? This is an inverse square law. The inverse square law relationship states that I is proportional to r to the power of -2. So that means to say, if r is double, then intensity will be 1/4. If r is half, then intensity will be 4 times. Okay, now, how do we make use of this? Now, we can also make use of this in the opposite way. R is proportional to intensity to the power of -half. Okay, so basically 1 over square root of intensity. Okay, so if the intensity is 4 times before, larger. So if the intensity is 4 times larger, it must be the distance has half. How come? Because R will be proportional to intensity, all right, which is 4 times larger, 1 over the square root of the intensity. So if the intensity is 4, then the distance will be 1 over 2, half. Okay? All right, so now, in this case, right, it tells us that the intensity of the source is half, and you want, sorry, let's take a look at the question. Now, the intensity of the sound source is half. Okay, after a while, the intensity is half. And you want to make it such that the intensity is as loud as before. So let me show you what is the situation over here. Here is the original speaker, all right? And here is the person who is listening to the song. Now the person is very happy because the intensity is just nice. Now, however, the speaker's power went down. Power went down. So what happened is that the intensity is now weaker. Oh no, the music got softer, I/2. So he's very unhappy. So what he does is that he moves over to here. Okay, he moves over to here where the speaker is, the power is still lower, but the intensity is back to I again. So basically he wants the intensity to double. The person wants the intensity to double. Now, what is the relationship between the distance and the intensity? So the distance will be proportional to 1 over square root of intensity. So if intensity becomes twice as much, then R will become 1 over root 2 of the, so if I2 is the twice of the previous one, then the R2 will be 1 over root 2 of the previous distance. So this means that R2, the new distance, will be 1 over root 2 of the original distance, which is 8. And that will give us 5.66 meters. Okay, well, alternatively, you can work it out by doing ratio. Okay, that if the power has half, then basically you need to stand closer to the receiver. But how much closer? Is 1 over root 2 as close as before. Okay, once again, if you're not sure about how this works, please ask me in class, and maybe I can approach this question in a different way, all right, so that it's maybe easier for you to understand. Okay, next, let's go to question 11, Malus law. A narrow parallel beam of unpolarized light is directed towards 3 filters. The beam meets the first filter with a plane of polarization vertical, and then after that, subsequently, more and more polarizers are tilted. Okay, now Malus law comprises 3 parts. Part 1 has the following rule. When unpolarized light passes through a polarizer, the intensity is half. Okay, so please take note, this only applies for unpolarized light. Pass through a polarizer, the intensity is half. This is the first part of Malus law. Now what about second part of Malus law? When polarized light, okay, passes through another polarizer, the intensity is reduced by what factor? A factor of cosine squared theta. Okay, cosine squared theta, where theta is the angle between the lights, the polarization of the light, and the axis of the polarizer. Okay, so let me illustrate this with an example over here. So over here we have unpolarized light. This is how I like to draw unpolarized light. So it's unpolarized light. And the unpolarized light has the intensity of 120 watts per square meter. Now it passes through a first polarizer, and the first polarizer is at an angle of 30 degrees to the vertical, 30 degrees. So this will be the first polarizer. Now, immediately when passing through the first polarizer, the intensity is halved. So now it's 60 watts per square meter, but it now becomes polarized light, and the angle of the polarization is 30 degrees. Now, let's move on to the next part over here. Okay, now this next part over here, the angle of this polarizer, the second polarizer, is 75 degrees. Okay, so the angle of the second polarizer is 75 degrees. Then what is the intensity of the light that comes out? I2. So how do we find out I2? I2 to the second polarizer, which is sometimes called the analyzer. Now I2 is equals to I1 multiplied by cosine squared theta. Now what is cosine squared theta though? Cosine squared, the theta is the difference between these two angles, between the angle of the light and the angle of the polarizer. So this will be equals to 60 multiplied by cosine squared 75 minus 30. Now if you put it into the calculator, the answer will be 30. So this I2 will be 30 watts per square meter at an angle of 75 degrees. Okay, so this is the end result of the two polarizers. Now let's take a look at the question over here. Right, so a narrow beam of unpolarized light is directed towards three polarizing filters. So over here we have unpolarized light, which I have to draw like that. The beam meets the first filter with a vertical polarization. So what comes out of the first polarizer will be a vertical polarized beam. The beam emerges with the intensity I and amplitude A. So this is the intensity is I and amplitude A. Now next, the angle of polarization is 40 degrees. That means to say there will be a 40-degree angle between the first and the second. So this is I2 will be I1 cosine squared 40 degrees. And what comes out will be a light at an angle of 40 degrees to the vertical. Now the next one is 90 degrees, but our light is at 40 degrees to the vertical. So the angle here, theta, will be 50 degrees. So we call this I3. Now I3 will be equals to I2 cosine squared 50 degrees. So this will be I1 cos squared 40 times cos squared 50. Okay, so let's finish up the entire table. All right, we'll do the intensity first. We'll do the intensity over here first. Okay, so the I2, as it comes out here, will be the original I, okay, multiplied by cosine squared 40. So we get 0.587I. Now then it passes through the next polarizer. The next polarizer, so now the intensity is I3. So I3 will be equals to I2 times cosine squared of 50. Why 50? Because the light comes out at 40 and the polarizer is at 90. The angle difference between them will be 50 degrees. So that will be 0.587 times cosine squared 50. That will be 0.242I. Okay, so these two are done. Now, how do we get amplitude from intensity? Remember that amplitude is proportional to the square root of intensity. So what we'll do is that we'll take 587I and we'll square root it. Square root of 0.587, okay, equals to 0.766. Right. Then over here, 0.242, we square root it, we'll get 0.492. So this is how the amplitudes decrease. So the amplitude is A here, and then after passing through the first polarizer, it will be the square root of cosine squared 40. It will be A cos 40 because you square root this, okay? Then that's A2. That's A2. Then to pass through the next one again, A3 will be A2 cosine 50 because you square root of cosine squared. All right, so every time you pass through, the amplitude reduces a little bit by the cosine of the angle. Okay, now what is the relation between the intensity and the amplitude of the beam after passing through each filter? The intensity is proportional to the square of the amplitude. All you got to do is to say this: intensity is proportional to the square of the amplitude. So deduce the intensity and amplitude of the original unpolarized light. Now what this question is saying is that, okay, this is the original filter, this is the unpolarized light passing through the filter at 0 degrees. After it comes out from the filter, the intensity is I. Therefore, previously the intensity must have been 2I. Let's take a look up over here. Now, after passing through the first filter, the intensity is I. So that means before passing through the first filter, intensity must have been 2I. Because of the first part of the law, which says that when unpolarized light passes through a polarizer, the intensity is halved. All right. So therefore, since the unpolarized light passes through the first filter, the original intensity of unpolarized light is 2I. And of course, the original amplitude, However, there's a slight difference in terms of amplitude. The original amplitude of the unpolarized light remains A. The amplitude is unchanged passing through the first filter. Now let me explain why the amplitude of the unpolarized light passing through the first filter is A. Now, in order to do this, we need to understand the nature of unpolarized light. Now, unpolarized light is made up of many different polarizations. It could be vertically polarized, horizontally polarized, okay, or polarized at any angle. Basically, you can be polarized at any angle. You add it all up together equals to unpolarized light. Let me just find out where I stopped. Okay, equals to unpolarized light with the electric field oscillating at any angle. So what happens when you pass the unpolarized light through a filter which is set at 0 degrees? Now, when you pass a filter, when you pass this unpolarized light through the filter, the vertical polarized light is okay, it passes through. The horizontal polarized light is not okay, nothing comes out. Okay? And then the two other polarizations, they come out, they will be halved because they are at 45 degrees. They are at 45 degrees, so the intensity is half. Okay, now let's take a look at the original intensity. Now let's assume that the unpolarized light is made up of 4 components, each with intensity I. Okay, so the unpolarized light has 4 components, each with intensity I. So the unpolarized light will have an intensity of 4I. When you pass the unpolarized light through a polarizing filter, which is vertical, 0 degrees, this intensity passes through with I. Vertical light passes through unchanged. Horizontal light passes through with intensity 0, and then light that is at 45 degrees passes through with intensity half I, thus giving rise to a vertically polarized light with intensity of only 2I. So you can see that the intensity has halved. But if you notice the amplitude of the light, okay, this amplitude remains unchanged over here. All right, and so you can see that although the intensity of the light is decreased, the amplitude of the light, which is made of the original waves, is unchanged. All right. Okay, so that will be the end of question 11. Once again, if you're unclear about this explanation, please look for me in class and I will explain it to you. Okay, it's not easy, that's why I'm recording it beforehand. Now, question 12 is about cathode ray oscilloscope. Okay, the cathode ray oscilloscope is basically an electric graph that would enable you to display a waveform on a screen. The diagram shows a trace produced by a sound wave on cathode ray oscilloscope, and the time base is calibrated at 2 milliseconds per cm. So that means that this 1 cm represents a time of 2 times 10 to the power of minus 3 seconds. So this will be our time axis in milliseconds. Okay, what is the frequency of the sound wave? Now let's take a look here at this one. This period, okay, is over here. So the period is 4 squares. Now the period is 4 squares, which means that it is 4 cm, which means that the period will be 4 times 2 times 10 to the minus 3 seconds. So the period t is 8 milliseconds, 8 times 10 to the minus 3 seconds. So the frequency of the wave will be 1 over 8 times 10 to the power of minus 3, which will be 125 hertz. Okay, and that's how to read a cathode ray oscilloscope. It's basically just a graph, which is electrical graph. And that is the end of our tutorial. Thank you and have a nice day.